Clifford algebra in 5 dimensions. So let's consider 5-dimensional Dirac matrices. The indices here will run from 1 to 5. Well, this is just the familiar Dirac matrices in 4 dimensions plus gamma 5, right? So they will form a 5-dimensional Clifford algebra. So now to go to SO6, we can do the following. We can use the following observation that if you consider matrices gamma ij, which are commutators of the Dirac matrices, and these are known to generate the algebra of SO5, right? Then we add Dirac matrices themselves, and we still get a system that's closed under commutators, because if you take commutator of gamma ij with gamma k, you get a linear combination of gamma k's. If you commute two gamma matrices, you get gamma ij, and they also form a closed algebra. So this set of 4-dimensional matrices form a Lie algebra, and this it is easy to convince oneself that this is nothing but SO6. So this is yes.
Gamma ij will have the commutator, but like, what is the precise prefactor defining gamma ij? Like, gamma ij is what times the commutator?
Sorry, I didn't.
Yeah, like I over 2 times
It's
commutator.
well, it's 1/4 of. You can normalize them properly so that they form the proper generators of SO5. So this actually works in any dimension, right? We can start with any odd-dimensional Dirac algebra, add Dirac matrices themselves, you'll get an algebra of in 1 dimension higher. But for SO6, there is an interesting twist to this story. Namely, if you count how many Dirac matrices are there, then, well, SO6 has 15 generators. So these matrices form a 15-dimensional linear space. They are traceless, and also they are Hermitian. And if you think how many Hermitian traceless 4x4 matrices are there, then you realize that they also form a 15-dimensional space, right? So there are 16 Hermitian matrices overall, and then one of them is just a unit matrix, so that we remove by the trace condition. So we can identify the spinor representation of SO6 with the full set of Hermitian traceless matrices of size 4x4. So this is complete basis in the space of Hermitian traceless 4x4 matrices, and well, this usually we identify this with SU group. So this space taken alone we would call it SU4. So this consideration then identifies the Lie algebra of SO6 with that of SU4. So in low dimensions, sometimes the different series of Lie algebras are actually one and the same thing. So One example is SO3 and SU2, SO4 and SU2 cross SU2, and this is another example. So the same is true for different signature. Without derivation, let me just state the result that SO, the Lie algebra of the conformal group can be equivalently represented as SU2, 2. Now, supercharges transform in the representation of these algebras, right? So they have Lorentz index, and so they transform under SO4, 2. And they have an SU4 index, so they transform under SO6. So I remind you that there are 4 supercharges. Each of them is a Weyl spinor. And their conjugates are transforming is a Weyl spinor of the opposite chirality. And it's also the conjugate representation of SU4. So when we go to the when we had conformal generators, so on the Lorentz side, we started with generators which were L-mu Lorentz transformations, translations. This would be Poincare algebra. But then we add dilatations and special conformal transformations to that. And this altogether forms SO42. So when we add supercharges, they of course nicely transform under Lorentz and translations and dilatations. So they are invariant under translations, transform as spinors under Lorentz. And they have scaling dimension 1/2, so they commute their eigenvalues of the adjoint action of the dilatations. So the question is, what happens if we act by special conformal transformations? So if you take a commutator K mu with a supercharge, what do we get? So this will be an odd generator. But by counting dimension, we see that it's a generator of dimension 3 halves. And there is no candidate in the superalgebra because all supercharges have dimension 1/2. So we need to add another generator which is called superconformal charge. Let's denote it by S. And okay, so since there is a vector index, we can write it as we can write it this way: alpha dot S alpha dot A. So these are new generators that we need to add to the algebra. And the natural statement is that if we add these generators, then the algebra closes. So one can reconstruct the full set of commutation relations just from this definition. And you don't need to add anything on top of that. So then a convenient way to package the commutation relations of the superconformal algebra is to form Dirac spinors out of Q and S. So we can add, so we can define theta as a 4-dimensional spinor that would, let me see. Does it work? I think that, let me check if I use correct notations. So usually this is called S bar. And and we combine it with Q to form a four-dimensional spinner. So Dirac spinner contains a left-moving Weyl spinner and then the right-moving spinner, and so this is a natural way to form a Dirac spinner. So we can denote the Dirac indices by A, where A runs from 1 to 4. And then we can put all generators of the superconformal algebra in a big 8x8 matrix. So the bosonic generators will sit in the diagonal blocks. And here, so it's convenient to multiply the conjugate by gamma 5. So then one can check that commutation relations of this supermatrix, which are defined by simply matrix multiplication, reproduces the commutation relations of the superconformal algebra. So in other words, the superconformal algebra can be identified with a matrix Lie superalgebra, which is called PSU2 2/4. Which is a matrix. So it's a matrix superalgebra that consists of this 4x4 blocks, where fermion parity is correlated with where the element sits in this block decomposition. So this 2,2 means that we need to pick particular real form of this algebra. Maybe I should explain what P means here. And this has to do with the trace condition. So when we define a unitary algebra, then we don't impose any trace constraints. SU algebra would mean that the trace of any element should be 0. But for supermatrices, the natural generalization of trace is supertrace. So if you have a matrix that has bosonic and fermionic blocks, then supertrace is defined as the difference between traces of A and B. And one can show it that this is this combination that's invariant under commutation relations, because they're also fermionic elements, so there is a minus sign here. So the trace condition then eliminates an overall trace in SU 2/2 and SU4, but not the individual traces of these elements. And this is because if you take a unit matrix then its supertrace will be still equal to 0. So SU algebra would have a central element proportional to unit matrix that obviously commutes with anything, but can only appear on the right-hand side of the commutation relations. So PSU2 is defined as an algebra obtained by modding out this central element. Yes?
I'm just wondering about the general matrix structure that you have on the top right of the second board. So, SU22, we identified that with SO42, so I imagine that that's corresponding to the just your conformal algebra, and then you've defined these capital thetas. But I guess maybe naively, I would expect the bottom right, like the remaining bosonic block, I guess, to be just another copy of the conformal algebra. Maybe you already explained this and I missed this, but just could you maybe comment on what this SU4 in the fermion block, I guess, is?
Yes. So let me comment precisely on that. So you see that theta is a 4x4 matrix. So it has 4 indices that I denote by lowercase letters and 4 that are uppercase. So they have different nature, right? So this index is acted upon by Lorentz generators, so conformal generators, and whereas this is an SO6 index. So we want, when we multiply these big matrices, we want generators of SU2 to act on theta from the left, but generators of SU4 from the right. And SU4 is SO6, yes. So with this structure, this is automatic. So when we take a commutator of such matrices, then SU2 will act on this lower index, and SU4 will act from the right, which means that it will multiply the upper index. So this is the structure of extended supersymmetry in 4 dimensions. The Lie algebra that is formed by all superconformal generators is PSU22/4. So this algebra has rank 7. Which, let me see if I can explain it. Actually, I don't remember why, because so each of its diagonal subalgebras, bosonic subalgebras, has rank 3. So you would think that there will be 6 generators, 6 commuting generators, but somehow you can add another one. I forgot what was the reason. But the fact is that you can choose 7 commuting generators in this algebra. So the Dynkin diagram of this algebra has 7 nodes. So you can and it also has additional elements that don't arise in bosonic algebras. So in addition to the bosonic roots, bosonic nodes, we have fermionic nodes. And also the links can be of 2 types. So to the bosonic node, we assign either the diagonal element of the Cartan matrix equal to either +2 or -2. The fermionic node corresponds to a 0 on the diagonal. And the link corresponds to, so the normal link would correspond to -1, and the dotted link to +1. So with these notations, the Dinkin diagram looks like that. So the rules of the game are following that once you hit the fermionic node, you should change the links to from solid to dotted, and also the diagonal elements change sign from 2 to -2. So let me maybe write the Cartan matrix as a matrix. So we start with this node. It has a -2 on the diagonal. There is one link to the next node which is fermionic, so it has 0 on the diagonal. Then the nature of the links changes. And then we get the usual SO6 Dinkin diagram. So this is the matrix that corresponds to this picture. So these 3 nodes correspond to the SO6 subalgebra. And the wings are associated with supercharges and with the Lorentz part of this symmetry. Yes?
Do you comment on what the /4 means?
Slash?
The,
Where? Oh, here.
Yeah.
So, yes, so, yeah, maybe I can give a definition what is SU MN is. So this is a set of matrices of the form AF F prime B such that trace A minus trace B is equal to 0. And well, the matrix is Hermitian. So the fermion parity of elements of these blocks is such that A and B are bosonic matrices, and matrix elements of F are fermionic Grassmann numbers. So when these are bosonic, these are fermionic. So we can imagine these matrices to be linear transformations on the space that is usually referred to as Rm/n. And this is a space where we have m-dimensional vector v and n-dimensional vector theta that are respectively bosonic and fermionic. So this is Grassmann parity even, and this is Grassmann parity odd.
So, but you also said that the P related to the trace condition, and so the
P, so if m is equal to n, then supertrace of unit matrix is equal to 0. So this trace condition doesn't eliminate the unit matrix.
I see.
And
Okay.
unit matrix commutes with anything. So it is a central element of the algebra, and we can mod out by it. So consider only the algebra without this unit element. So what naturally comes out of the packaging conformal algebra and subcharges into the matrix doesn't have a unit matrix in it, so we need to consider PSU into 2/4. Yes? Yeah. Yes. Any other questions about this algebraic part? Well, if not, then we can immediately write down the answer for the full spectrum of n-equal supermeals, because that only depends, for that we only need the Cartan matrix and the Dynkin labels of the field representation. So, and those are given here. So for Cartan, for the Dynkin labels, we can guess that it's the same as for SO6, right? For SO6, we only had this middle part, so we just complement them with 0, and that defines a set of beta equations. That describe the full spectrum of supermeals at one loop. So let me, I wrote these general beta equations that are valid for any Lie algebra, and they extend to superalgebras. So let me repeat them here. And the energy is, so the energy is the anomalous dimension. That will be equal to lambda over 8 pi squared, sum over alpha j, q alpha. So there is only one momentum carrying node, so we could have immediately written the formula that only contains roots on the 4th node of the Dynkin diagram. That only them contribute to the energy and momentum. So this describes all possible states of n=4 superyoung meals. I will not give any examples of how to compute solutions of these equations, but let's just see what are the elementary Magnon modes that correspond to, well, individual roots of individual root solutions. So in principle, we can consider solutions where we put any number of roots on each node. But since most of these nodes are auxiliary, there is a restriction that the number of roots in the middle node is larger or equal to the number of roots on the wings. And the reason for that is that only modes on this node create real physical magnons. So the other beta roots, they only change the flavor of the existent excitations in the spin chain. And so you cannot apply, for instance, this root on its own because there are no excitations to begin with. So you need at least one root here that would produce a physical excitation. So let's count how many excitations we have in the simplest case where we have only just one magnon. So then we need to put one excitation on the central node, or and then we can decorate it with roots on the wings. So for instance, we can consider this configuration of roots, or this, or that, and so on. So let's just do the counting and see how many states we get. So let me just claim the answer. You will probably, once I write it down, you probably will see how it arises. So the claim is that the number of excitations is equal to 4 squared, which is 16. So the reason is that so all elementary excitations are strings of ones that should stretch through the middle node, and they should be continuous. So we cannot put one here and then a 0, right? So this number is equal to sum from alpha to, so each string will have a beginning and an end point. So let's denote by alpha its beginning, which can be anywhere between 1 and 4. And then the end point will, since the string should pass through the fourth node, it should be either 4 or a bigger number up to 7. And we sum with the weight 1. So this sum is equal to, well, 4 times 4, which is 16. So out of these 16 modes, half will be fermions. And fermion excitations correspond to the ones that cross the fermionic node. Or more precisely, those that cross fermionic node odd number of times, because there are 2 nodes, so there can be an excitations that, the excitation that goes from, for instance, from this node to that node will be, again, bosonic. And one can see that out of the 16 modes, 8 will be bosonic and 8 will be fermionic. So what do this mode correspond to? Well, they correspond to assertions of some elementary fields inside the spin chain. So we start from the ground state, which is a chain of Z fields. And then we cross one of these fields and replace it with some excitation phi that can be either bosonic or fermionic, and it has two indices. Let's denote them by A and A dot. Well, so now these indices run from 1 to 8. So what are these fields? Well, it is very easy to see what do they correspond to. So let's start with the bosonic fields. So there are originally 6 bosons, Z, Z bar, and then 4 other bosons that we can parameterize by letters A and A bar, where A and A bar and A dot run from 1 to 2. So the reason to separate these 4 modes from to distinguish them from Z and Z bar is that Z bar is a composite excitation, even in the SO6 spin chain, and Z is just a vacuum state. So real excitations, there are 4 of them, and we can parameterize them by complex 2 by 2 matrix. Then we can add by derivatives on Z, and derivative can be expanded in the basis of Pauli matrices. Right, so it has 2 indices again that run from 1 to 2. And fermions, one can show that they have the same index structure, so they can have either one undotted index and the other dotted index, then, or vice versa. So in total, we have 4 plus 4 bosonic excitations and also 4 fermionic excitations. So the structure can be also inferred from symmetries alone, because when we consider the basic vacuum operator build of Z, that breaks the superconformal symmetry, so the ground state is not invariant under superconformal transformations. It is not even invariant under SO6 because Z picks a direction in 6-dimensional space. But it's easy to see what is the remaining symmetry group. So since we sort of place excitations on top of the on top of this node. So this node only creates physical magnons, and the nodes that are responsible for symmetries, so the symmetries under which these excitations transform, are the wing nodes that do not carry energy and momentum. So to find the algebra of the unbroken group, we just cross this node. And what remains is the Dynkin diagram of the Lie algebra of PSU2 /2 squared. So maybe, I don't know, maybe this is not very, it's a little bit abstract. Let us see how this works in this middle SO6 part of the diagram. So if we start with the with 6 fields and single out one of them, what is the symmetry that will be unbroken by that will remain unbroken? So we pick a direction and consider all transformations, all SO6 rotations that preserve Z. So can you immediately see what this group is? So Z is a complex field or complex vector. What are the, in 6 dimensions, what are the, what is the symmetry of a 6-dimensional complex vector? SO4, exactly. So a complex vector has a real component and a imaginary component, which are 2 vectors, and in this case, they're perpendicular to one another. So a complex vector is actually defines a plane. And symmetries of a plane in 6 dimensions is rotations in the perpendicular space, which is 4-dimensional. So, so this group is SO4, and SO4 is, well, at the level of algebras, it's just equality, but basically, roughly speaking, SO4 is SU2 cross SU2. So symmetries that are preserved by picking up one of the fields, Z, is a product of 2 SU2 algebras. And these are precisely the algebras that rotate these 2 indices. So these are the indices over the unbroken SU2. And at the level of the Dynkin diagram, again, we take the Dynkin diagram of SO6, cross one node. What remains is 2 circles, and this is the Dynkin diagram of SU2 cross SU2. So if we add supercharges, then each of these SU2s is extended to a superalgebra, which is called PSU2/2. So we can actually understand how the superalgebra acts on the elementary fields. So we can draw, it's as usual in supersymmetries. You can always picture supersymmetries on a diamond diagram. So we can place place all the fields on the vertices of a diamond. And then one PSU2 to say PSU2 to right will act in the south east direction, and PSU2 to right will act in the southwest. So one can see that the same structure of excitations and the same symmetries arise when you quantize string theory in the light cone gauge. I'll not explain it in detail, but just counting the degrees of freedom, you see that it should match, because if you start with supersymmetric string in 10 dimensions, the number of transfers physical degrees of freedom is equal to 8, right? Because temporal direction is unphysical, and then you can also fix another one because you fix the gauge. So what remains are 8 transverse fluctuations of the string. By supersymmetry, they are related to 8 fermionic modes of the string. So the string spectrum also consists of 16 degrees of freedom, half of them bosonic, half fermionic. So if one carries out this quantization procedure in AdS 5 cross S5, one can also see that the symmetry structure comes out precisely in the same way. So the unbroken symmetry is PSU22 slash times PSU22, and the excitations of the string belong to the bifundamental representation of this algebra. So, in fact, one can interpolate between field theory and string theory descriptions using beta ansatz. And maybe I'll say a few words how the how integrability works beyond one loop at the non-perturbative level. I have no time to explain it in any detail, so I'll just overview what are the salient features of the beta equations. How much time? 40 minutes. Okay, very good. Any questions to this part? Yes.
Thank you. So is the main lesson of this calculation that the superconformal symmetry is broken in a specific way, or what was like the main lesson of this one loop calculation?
Well, this symmetry breaking pattern is not related to any dynamics. It's just it arises because we chose a particular operator as a ground state. So we say that our ground state is associated with operator trace z to the L.
Okay.
And then basically classify symmetries that preserve this operator. So it's a purely kinematical statement. There is no dynamics or loop corrections involved.
Okay.
And therefore it stays the same to any loop order.
Okay. Thank you.
All right, so let me describe mostly in words what happens at higher loops. So the salient features remain the same. So there still will be some beta equations with the same degrees of freedom. So the roots of the beta equations that are the unknown variables will be associated with the vertices of the Dynkin diagram. But the kinematics changes. So both the left-hand side and the right-hand side of the beta equations will receive loop corrections. And also the formula for the energy will be a bit different. So the left-hand side is basically the e to the momentum times length. So this is the wave function part of the beta equations. So momentum will depend on rapidities, but also in a way that is deformed by the coupling constant. So the right-hand side corresponds to the S matrix. And S matrix, as you may imagine, it also depends on the coupling constant. So the way magnons scatter will be affected by the loop corrections. So all of this can be sorted out. And the way it is done is, well, doesn't require any loop calculations. In fact, one can infer everything by smartly exploiting symmetries of the problem. I will not tell you how, but just write down the answer. So first, let me tell you what happens to the elementary excitations of the spin chain. Well, in perturbation theory, there's some magnons of the Heisenberg spin chain, well, dressed by other symmetries. So they have quantum numbers of some supersymmetric algebra, but the dispersion relation is the same as for magnons of the Heisenberg model. So let me write it down like that. So in the when we derived it, we didn't have this one here. But the reason I write it in this way is because I want to go from Hamiltonian, which is associated with the dilatation generator. Right? So it measures the scaling dimension of the corresponding operator. So instead of that, of the pure dilatation generator, I would like to use the difference between dilatation and the R charge. So this R charge is basically so what we called J1. This is the generator that rotates the phase of the field Z. Okay, so when we insert a magnon, we replace a Z with a W. So we diminish the R charge by 1 unit. So that the scaling dimension will change because there are quantum corrections, so it will acquire the anomalous piece. This is this term. But also there is a trivial, if you consider this as a Hamiltonian, there is a trivial contribution from changing the R charge of the whole system. So this is what happens at weak coupling. So at strong coupling, we should consider, well, the string that propagates in AdS 5 crosses 5. So we'll have a closed string that somehow moves in this space, and at the same time it can rotate and oscillate. So the one way to quantize the system is to fix the, say, some physical gauge, like light cone gauge, then expand the string action in elementary fluctuations and quantize them as fields in the two-dimensional worldsheet. So this will define some 1+1 dimensional quantum field theory. So the elementary string excitations will then be particles that propagate on this two-dimensional worldsheet. And, well, these particles will have, to the leading order, you may expect that they will have a relativistic dispersion relation, p squared plus m squared. You may be more familiar with the case where they are massless. So if you consider string theory in flat space, then string modes are simply free massless particles propagating on the worldsheet. So in AdS, we need to take into account curvature. So both AdS5 and S5 are curved. And curvature turns out that it contributes to the energy of elementary excitations in such a way that it produces a mass for these particles. So this comes from curvature of AdS5 cross S5. So at the technical level, what happens is you consider first the motion of the center of mass of the string, and then you expand. And when you expand, say, the kinetic energy of the string around the geodesic, then there are quadratic terms in the deviations that are proportional to the curvature tensor. And so once the curvature tensor is non-zero and constant, you get simply a mass term. It's m squared x squared type terms in the Lagrangian. So all in all, what we get is a set of 16 transverse modes with this dispersion relation. So the exact answer should somehow interpolate between this formula at weak coupling and this formula at strong coupling. So let me just write down the answer. So of course there is no unique way to write it, to write a function that would interpolate between these two limits. Instead, what one can do is one can look at representation theory of the unbroken algebra, which is PSU2 squared. And it turns out that just representation theory uniquely fixes the dispersion relation, which happens to be just the square root of the three-level answer, in a sense. So if lambda goes to 0, then you get lattice dispersion relation for magnons. Whereas if lambda goes to infinity, well, you need to rescale p, so you should take into account that momentum on the string worldsheet differs from the momentum on the spin chain by this factor. Again, don't remember a simple explanation for that. And it probably requires to carefully go through the gauge fixing procedure, but there is a rescaling factor here. If you insert it in the dispersion relation and sense lambda to infinity, what you get is simply a dispersion relation for a particle of mass 1. So the interpolating formula is something in between. So on the one hand, it is periodic in momentum, so it's definitely a lattice type dispersion relation. The momentum is periodic, meaning that the system is fundamentally discrete. On the other hand, it has features of relativistic symmetry, but with p squared replaced by sine p squared. In fact, one can actually formalize that in some way. So it turns out that the whole structure of this, say, this string action is invariant under some kind of deformed Lorentz symmetry. So if you take into account all interactions on the world sheet, then what you get is they will break the naive Poincare symmetry in 1 + 1 dimension, but instead they don't break it completely, but rather Q-deform it, and this produces this lattice type dispersion with this sine term. So then the other ingredient that we need is the S matrix, and that turns out to be also fixed by symmetries completely without any further requirements. Well, one needs to impose the condition that the S matrix is unitary, crossing symmetric, and invariant under PCU22 squared, and that's enough to fix it completely. The answer, well, it's not particularly illuminating, it's rather complicated formula, so I will not write it down, but just describe it in words. So the elementary fields that we scatter they can be combined into an object that transforms in bifundamental representation of PCU22 squared. So when you scatter these two of these objects, so the S matrix, so you start with two fields with indices A dot and B dot, and produce two other fields with another 4 indices. So in total, the S matrix will have 8 indices transforming under different groups. And integrability doesn't like that much. So the only way you can satisfy all the constraints of integrability, factorization, and crossing symmetry, etc., is to accept that the S matrix factorizes, so that it is a product of individual scatterings for each of the for the left and right PCU2 two subalgebras. So this matrix will be a product of two elementary S matrices. And each of these factors, it depends on two momenta, and it can be found from symmetries. So it's known as Bizard's S matrix. And it is invariant under PSU2/2 symmetry. So it is known explicitly. Well, expressions are not very simple, but it's just an explicit formula in terms of momenta and it's written in terms of elementary functions. So there is a nice way to package this kinematics, which allows to write down the beta equations in a nice way. So, so as I said, that the dispersion relation is somewhere in between relativistic and lattice. And there is a way to parameterize it. So there is a nice way to write down this dispersion relation in one simple formula that introduces what is known as Zhukovsky variables. Which are defined in the following way. So the basic variable is rapidity. This is the same variable that will appear in the beta equations. So it parameterizes the energy and momentum of each individual magnon. So, but one can also map it to a variable that's called x, and which is defined by this formula. So at weak coupling, when we set lambda to 0, there is no difference between x and u, but then you need to take into account quantum corrections, and they produce this term. So if you draw what is the out of natural domain in which these variables are defined, then you can see that this map is this maps defines a transformation of the U-plane in which so you draw a cut from minus square root of lambda divided by 2 pi to square root of lambda divided by 2 pi. So when you solve, when you invert this transformation, you will need to solve a quadratic equation. It's quite natural that you get a square root cut. And the exterior of this plane is mapped to the exterior of the unit circle. So this is how Zhukovsky map is actually defined. It maps a plane with a cut into exterior of the unit circle. So the x variable lives on the outside of the unit circle in the x plane, and in the u plane, any value of u is allowed, but there is also a cut along the real axis. So if you define, so then it's convenient. Yeah, so if you look back into the dispersion relation of the magnons in the Heisenberg model, let me write them down. So the momentum of the magnon in the spin chain is parameterized in terms of rapidity like that. And the energy of the magnon is, well, basically up to some prefactor, it's 1 over u squared plus 1/4, which is, one can write it as u divided by u minus 1/2 minus I divided by u, so let me see, plus 1/2 minus I divided by u minus 1/2. So you see that shifts by 1/2, shift by 1/2 is a very natural, operation on the rapidities. And so to generalize it to all loops, we defined these shifts for the x variable. So we define x plus minus of u as x of u plus minus I over 2. And then the claim is that the formulas remain the same, that e to the I pi is x plus divided by x minus, and the energy is I over x plus minus I over x minus. So I claim that if you solve these equations, so if you exclude u from these equations, you will get this square root type dispersion relation with the sign of pi. But so basically the sorry.
You swap u and x in the definition of the problem.
Ah, yes. It's always dangerous to have someone who knows. Huh? Yes, this is. How should I? Let me cross this equation. So it's u that's equal to x plus lambda over 16 pi squared x. Then x of u, you can express x through u. This will contain a square root cut. And indeed, you can see that yes, so if, yeah, to see this picture, we can parameterize x. Let's say that if you take x to be, so this is not a unit circle, it's circle of radius square root of lambda over 4 pi. Right, so if you write it as square root lambda x equals square root lambda over 4 pi times e to the I phi then u will be equal to square root lambda over 2 pi times cosine phi, right? So if you go around the circle here, changing phi, then you will make two oscillations between these 2 points, right? So it will first go around the upper shore of the cut, and then it will go back along the lower part of the cut. So and then if you make so going up to the outside of the plane corresponds to giving x an absolute value bigger than square root lambda over 4 pi. So the claim is that the beta equations basically they are deformed basically in two ways. So you need to replace u variables by x variables in the on the left hand side, but the right hand side to some extent remains unchanged. So I'll write only SU2 sector beta equations. So so they will look like that. This is what we should write on the left-hand side, because this is the momentum of the magnon, e to the momentum of the magnon, and then we raise it to the power L, we get e to the e pi L. So that should be equal to the scattering, should be compensated by the scattering shift of magnons. And that is basically not changed by the loop corrections, apart from an extra phase that is known as the dressing phase. And which has a relatively complicated form. So theta of u v is equal to sum of our s plus minus and for chi one can derive the following integral representation, which I don't remember by heart. So so strange enough, this complicated formula can be derived solely by symmetries. It's essentially this phase factor restores crossing symmetry of this matrix by using the, in this particular semi-relativistic kinematics. So you see that the beta equations, well, they acquire this additional phase, and also the kinematics that relates rapidity to the momentum changes. Apart from that, they have the same form as at one loop. So one can show that, so you see that this phase vanishes when lambda goes to 0, because then, well, this essentially the shift here disappears and the logarithm produces 0. In fact, I think that the first correction comes at order lambda cube. Whereas the corrections to the dispersion relation, they start to be important already at 2 loops. So if one goes to the strong coupling limit, the same beta equations describe the scattering of elementary excitations which become relativistic in the limit on the string wheel sheet. Yes? So yes, there is a minus here and a plus here. So that's the difference.
And how do you read the lambda large limit in that expression? If the limit is simple, if not, it's just that. But
how? I forgot. But it's it starts to. I mean, it is important that so it has a non-trivial strong coupling limit. How does it work? You need to use the Stirling formula for gamma, then do the integrations, and that produces some non-trivial function. Yes, so I will stop here. So this none of these formulas I was able to derive, but the derivation will is well, it not a trivial step, but again, the only thing you use is just symmetries. So all of this, once you believe that the system is integrable, integrability is so rigid that you can reconstruct the answer just by employing basic principles of what you expect from basic principles of unitarity, crossing symmetry, and you need to exploit all possible symmetries of the problem. In this case, supersymmetries. So as far as what is known is not known, and not known is that spectrum. So this is just part of the set of spectral equations. So it only describes operators made of Z and W. But there is a more complicated but longer system of equations that describes all possible operators at any value of the coupling, and it smoothly merges with the string spectrum at strong when lambda is large. What is less known is how to compute correlation functions, for instance. If you want to so the Scaling dimensions only fix 2-point correlators in a conformal theory. To compute 3-point and higher point correlation functions, you need an extra ingredient, structure constants of operator algebra. So there is very interesting ongoing work on how to calculate them using integrability, but it's mostly work in progress, which is not finished yet. So thank you very much. I finish here.
Some more questions for Kostya.
Maybe not too much related to the content, but in the way or in the method to fix this using symmetries, what are the mathematical tools involved? Is it just representation theory, or you have some other inputs?
Mainly representation theory. So you need to, yeah, so for instance, to fix the S matrix. The S matrix is an operator. Well, it's a matrix, so it takes you from the tensor product of two representations to the same tensor product. And invariance means that it's an invariant tensor with this structure of indices. So it turns out that there is just unique invariant tensor for PSU22/2. So you cannot write anything else. So there is just, that fixes S matrix to be just number times fixed tensor structure. So this number, of course, is not fixed by symmetries alone, but this matrix has to be unitary and crossing symmetric. And so crossing symmetry and unitarity gives you one functional equation. And so this is not just a number, it's a function of external momenta. So you get a functional equation that fixes that, that sort of shows you what happens under discrete shifts of the kinematic variables. Actually, this phase is basically the solution to this finite difference equation. It's a minimal solution. So it's simply, yes, it is representation theory. It's tensor analysis for PSU2/2.
Any more questions or comments?
I think there is a question here.
So I was wondering, is this kind of construction that you showed us for n equal to 4 super young males in 4 dimensions, are there any other examples of this kind of constructions, for instance, in lower dimensional gravities or other dualities?
Yes, so this same procedure works for ABGM theory, which is a conformal theory in 3 dimensions, and it is dual to strings in, so it's D equals 3, N equals 6, supersymmetric gauge theory. This is dual to AdS4 cross CP3 string theory. And that can be solved along the same lines. So there are also strings on AdS3 cross S3 cross T4, or AdS3 cross S3 cross S3 cross S1, which carry the same integrable, very similar integrable structure to AdS5 cross 5 and AdS4 cross CP3. It's not quite clear what they're dual to. And That's one of the obstacles. But the spectral equations have been written, actually very recently, for this background. And they're a little bit different from AdS 5x5 and AdS 4x CP3. In particular, there is no limit in which they describe a spin chain. So they always remain sort of stringy. So yeah, the short answer is yes.
Okay, then I want to follow up and ask, so does any, like, kind of, so whenever we have like a theory with a gravitational dual, does these structures carry over? Or there are known examples where this doesn't work?
There are certainly many examples where it doesn't work. Integrability is a very, very constraining and a very rare property. So it's most systems are not integrable, and most string theories are not integrable, in particular those that are dual to well, describe holographic duality. So I think that what Carlos was talking about is certainly not integrable. I mean, so it's only the very symmetric isolated points in the moduli space of all holographic dualities that are
There's
integrable.
a very symmetric has like a precise mathematical characterization, or we still don't have that?
Well, probably not very precise, but just by experience, it should have maximal possible symmetries out of.
Kostya, there seems to be a question in the chat that is a bit of a follow-up from this one, and is which aspects of the construction you develop survive or generalize in models where SUS is broken?
So supersymmetry here, supersymmetry, per se is not really important here. There are examples where supersymmetry is broken, but basically the way to break supersymmetry but preserving integrability is to by imposing boundary conditions on the string. So you can consider, well, there are ways to systematically deform boundary conditions on the string. So you originally consider closed strings, but then you can do some transformations involving change of the boundary conditions. And that produces a non-supersymmetric theory that is dual to non-supersymmetric conformal theory in 4 dimensions. But secretly, it's still the same. So the same, from integrability point of view, it's the same structure. So their beta equations change very little by some extra phases. But yes, there are examples that are not supersymmetric but still integrable, and which have a well-defined AdS counterpart.
Any more questions or comments? Okay, thanks very much, Costa.